I'm going to talk today about laser scanning, and we're going to talk about it in an applied context, which is mapping this coastal defence structure in Porthcawl. So we've got a breakwater down there with a lighthouse on it, and then this wall, and it was all built around 1826, and over the years it's been battered by the sea, and the increasing intensity of winter storms means that the structure is actually starting to break down. It was never designed for that sort of beating. So what can we do to measure it? Well, we can have fixed points on the wall, and then we can measure how those change over time. But what about the bits in between those points? That's where this technology of 3D laser scanning is really useful. So we'll start off by introducing what is laser scanning and what is the deliverable, what is a point cloud. Then we'll look at this particular instrument and its capabilities, and then we'll look at the limitations of what this scanning technique and methodology means. So if you imagine on a map you have a coordinate, and a coordinate has an X and a Y value, and that puts you on a point in a two-dimensional space. If you introduce a Z value, that's the height, you end up with X, Y, Z. So that's a three-dimensional point above on your map coordinate system. So a laser scanner actually measures 3D coordinates, but rather than just getting one point, it's capable of measuring between 50,000 and 1 million points every second. And this is what we call mass data capture. Another way of looking at it is reality capture. So the ability to mass capture millions of points very, very quickly and very accurately means that we can 3D visualize in a digital sense big structures like this. Okay, so this is a terrestrial laser scanner or LiDAR instrument, and this one's made by Topcon, and it's called the GLS-2000. So I'm going to talk through the main components of the scanner. So it sits on a tripod, just like a camera, and it has to be perfectly level. So we get it roughly level, and then we use these screws to get it bang on. So just like a camera, it's got a lens, and the lens is actually inside here. We've got this rotating mirror that picks up the laser source, which is transmitted inside this part of the instrument, and then it hits the mirror and it's transmitted off to the surface that we're measuring. And what the instrument does is measure the time it takes for that transmitted pulse of light to come back. So that two-way travel time at the speed of light is solved in terms of the distance. And to gather the many, many points that make up a point cloud, this mirror spins round very quickly, and the instrument slowly rotates through 180 degrees. And that gives a full dome of 360 degrees of data. The reason it only rotates 180 degrees is because the mirror measures through the front and the back simultaneously as it rotates. So how does it actually get the distance? Well, it knows the horizontal angle, and it knows the distance from, just like the distos that we use in DIY, and then it also knows the vertical angle. So using those three components, it's able to solve the three-dimensional coordinate, which I just explained, of any distant point. So just recap on that. The instrument rotates slowly through 180 degrees. It's transmitting up to 1 million points every second, and it's measuring a three-dimensional coordinate through a whole dome of data within the range of the instrument. Now, this is a mid-range instrument, and the furthest that it can feasibly measure is around 300 meters from this point. This is where we run into one of the limitations of laser scanning, and that's because to get a good data point at a good distance, we need a good reflectivity of the surface. And what that means is if it's bright, we get a good return, and if it's dark, we get a poor return. So there's a those white signs on the breakwater over there will give brighter reflections than the darker bits covered in seaweed. And right at the worst case, if we've got wet rock with black algae on, that may not give any returns at all. But on the whole, this is a very good surface. It's quite bright. And so within the full sphere of that data, we'll get up to 300, maybe 350 if we're lucky, meters of data. And in terms of timing, to do a 3D survey from this point, for one rotation, we're looking at about 3 minutes for the total capture time. And then we can move on to another survey location. And we'll come to that process in a moment. But there's one other component of these laser scanners, and that's this other little lens here. And this is an actual wide-angle camera. And it's possible to acquire not just 3D data points, but also 360-degree photography. So if we choose that option to take the photographs, the first thing the instrument does is just move around in about 8 positions and take a wide-angle photograph to give us a 360-degree mosaic of imagery. And that imagery is a useful visual record for where this survey point was, but it's also used to colour the points. So we can have points either coloured by the intensity, which is the amount of light they reflect, or we can colour them by the true RGB values, as we call it. So this will look really like virtual reality, very realistic once we look at the 3D model in the viewing software. So set up on the point, decide on the parameters for the survey, and that is the density of the points. So we don't want to capture too many data points, and the density is expressed on the instrument in terms of the spacing between the points at a distance of 10 meters. And at the moment it's set for about 3 millimeters at 10 meters. That's probably still a bit of an overkill for this data set, so we could open it up and that would speed up the actual survey time. But realistically, when we're modelling these surfaces, point spacing of around 12 millimeters is fine. And since we're talking about resolutions, what's the accuracy of this instrument? So at a distance of about 100 meters, we're looking at plus or minus 2 millimeters of accuracy. So if we've got a surface like that, we'll get 2 millimeters either side of it. And that's pretty good for this sort of range, and it's perfectly acceptable for monitoring these sort of structures. And the beauty of this technique is that because we've got this mass data capture and we've got that sort of accuracy, it means that we could come back here in a year's time, maybe after a season of winter storms, and we can measure the same surface, and then we can compare the two. And we can see areas that may have moved, even individual blocks that have been forced out or moved in the wall. And that gives us a much greater insight into how this structure is actually behaving and reacting to those forces of nature than if we were just measuring discrete points at, say, 10 or 20 or 50 meters using conventional survey techniques. 3D scanning is an optical survey tool, and what that means is it can only measure what it can see, or we can't see round corners. So when the survey method is setting up on one position and acquiring the data in the 360 degrees and then moving on to another location where we get a different perspective on the target that we're mapping. So on this sort of survey of a big structure like a seawall, I like to go up maybe 40 or 50 meters between stations. So in this case, that would take me over there and I'd be able to see around the corner of where that bend in the wall is. And then I would get the missing data that I can't get from here. If I was just to look at the data from this one position, I'd see a shadow behind the wall for the bits that we can't see. So this raises the next challenge in scanning, which is planning how you're going to do your survey, but then also thinking, how am I going to join those successive scans together to give a complete data set that all fits together. And that process of linking scans is called registration. And there's a couple of ways that we do that. And the first way is really easy. It's called cloud-to-cloud registration. And what that does is using the powerful software for processing point clouds, and that's a real advantage nowadays, is that our laptops are powerful enough to do this sort of thing. It looks at the geometry and the unique shape of parts of structures that we've mapped, and it identifies that in successive scans, and then it matches them together. So it's shape fitting, taking the shape from one scan and another, and then fixing them together, and retrospectively solving the position of the scanner. So that's cloud-to-cloud registration, and it works really well. It's pretty much one click of a button in the software, but it's dependent on having good overlap between the scans. And typically we want to think 20–30% overlap is good enough. The other method for registration is called occupation and backsite, and that relies on occupying a known position with the scanner. So we might have a survey peg banged in the ground here, and we've picked up its coordinate using a GPS or a total station. And that coordinate is usually in a local grid system, and in the UK we use the Ordnance Survey National Grid. And then we need to backsite onto another known point. So that could be another surveyor with a reflective target over another known survey peg. So we, just like a total station, rotate the instrument and we roughly sight onto the other point. And actually got the camera to help us in that process. And then we just simply take a measurement, and it will measure the angle and the distance to that other point. And that will then fix this position and the orientation of the scan in Ordnance Survey National Grid coordinates. And what that means is then when I move to another position, again over a known point, and sight onto another known target, we get the exact coordinate of that point as well. And that's another way of joining together successive scans, and not necessarily with the need for overlap. If we didn't know the coordinates, if we were working on a local survey grid and we wanted to change them afterwards, then we could bring a GPS, an accurate differential GPS, and measure afterwards our known points and put them on the OS or latitude and longitude grid. So that's how we geo-reference our scans, so we can relate this structure, this seawall, and the aspects of this beach to the map of the country or the map of the world.
Okay, so we've completed the survey on the beach, we've downloaded the data from the laser scanner, and then we've registered it in the proprietary scanner software. Now I'm going to run through some of the common deliverables and talk about how we can present LiDAR data. The first one, which is the most basic, is a raw Xyz point cloud. And that can be a PTS format, a file called LAS or XYZ. These are all essentially the same, and they contain XYZ coordinates for each of the points in the point cloud, and then optionally an intensity and an RGB color value. These point clouds can be imported into a 3D viewer. It could be a standalone application, such as Point Tools or Recap, or it could be a web application. I recommend Autodesk Recap because it's free, it's very easy to use, and it allows basic editing of your point cloud to remove any unwanted data, and then for that to be saved and possibly decimated into a format that can be used for in other Autodesk applications like Revit. Another deliverable, which is very common, is to render a high-resolution video or static views of the point cloud. And this can be very good for communicating a scene, maybe in a courtroom or in a meeting to stakeholders on an engineering project. But it requires no specialist software, and it can also be embedded with other presentations. If we take the point cloud and we create a 3D surface mesh, we can then use that for engineering analysis. We could use it for looking at displacement studies. So I mentioned that seawall gets a lot of damage from coastal erosion. If we were to repeat the survey a subsequent year or 2 years down the road, we could look at how the surface mesh, the shape, varies from scan to scan and see if any particular parts of the wall are failing or moving. And then lastly, we can take the point cloud and then either manually or semi-automatically extract line work. And that line work can be presented as a two-dimensional elevation in an AutoCAD drawing, or it could be converted into a 3D model such as Autodesk Revit, which is used by architects and engineers for design or to look at the as-built properties and geometry of that surface. This is an example of an animated fly-through of the point cloud. And you can see without any specialist software, it shows the real high detail of the cloud and how we can present it. This is the data from Porthcawl in a web viewer, and it's called Magnet Collage Web from Topcon. And what this enables us to do is to interact with the point cloud. You can see each of the scanner positions as these green dots, and the coloured point cloud is viewable by just simply navigating around with the mouse. If I zoom right in, you can see the data represented as millions of coloured dots. And we can create any viewpoint that we want. We can switch between a perspective or an ortho plan view of the site. And we can also change the way that we render the points. So if we focus in on this bit of wall, within this software, we can switch from RGB color to two types of intensity. The first one is Grayscale Intensity. And this enables us to see a lot more detail without any shadows or anomalies from the photography in the point cloud. And remember, I explained that intensity is a representation of how reflective the surfaces that we scan actually are. And we can also view intensity in terms of color. And if you remember, I mentioned that poorly reflective wet surfaces or dark surfaces they have low intensity, and that's what we see on wet bits of the wall where there's actually water seeping out. So that could be a clue for where there is erosion and water being retained behind this structure at high tide. And then another way of presenting it is by elevation, and this simply colours the point between the range of the lowest and the highest points in the data set. And you can see the range of the instrument. This particular one can measure points up to 300 meters away, and some of the scans on top of the sea wall have actually picked up surrounding buildings and some of the boats in the marina. And these aren't necessary for our survey of the seawall, but they're nice to give it some kind of context in terms of what we measure and nice in visualizations. But if we were doing some 3D modeling on the wall or some engineering analysis, then we could actually use some editing software and remove the unwanted points, reduce the size of the data set, and just focus in on what it is that we want to analyze. So that's Topcon Collage Web, and what I'll do is share a QR code, and if you scan that on a mobile device, you'll be able to open up this in a browser and have a play with it yourselves and see what you can actually do with the point cloud.